Today we are going to do elasticity. Suppose this is a wire and the wire is pulled by a force F from both sides. So when the wire is pulled by a force F from both sides, then if you consider any cross section of the wire, then for any cross section the two sides of the cross section, they exert equal and opposite force on each other. So this is a wire, it is pulled by a force F on either side, and if we consider any cross section of the wire, then both sides of the cross section exert equal and opposite force F on each other. So the tensile stress is defined as F divided by cross section area. So tensile stress is F by cross section area. Tensile stress comes under the broad category. Tensile stress comes under the broad category of longitudinal stress. So longitudinal stress is basically of two types. Suppose if we exert a force F on both sides of the wire to compress the wire, then for any cross section, the force exerted by either side of the cross section on the other is equal and opposite force F, and the compressive stress is defined as force per unit area, that is F by A. Now compressive stress and tensile stress, they both come under the category of longitudinal stress. So whenever a wire is subjected to an external force, either in terms of extension or in terms of compression, then a stress is built up inside the wire, but the wire needs to have the property to resist this elongation or compression, and it can do so by these restoring forces which are developed internally within the wire. And this property of the wire to restore itself or to resist any change in its shape, be it elongation or compression, this property is known as elasticity. Just like longitudinal stress, we also have volume stress. So what happens is, that Suppose if there is a fluid and if I consider an element of the fluid, it is exerted upon by a force F. So this force per unit area is known as volume stress, but because we are talking about a fluid, then force per area is better defined if we call it as pressure. So the volume stress for any fluid is nothing but the pressure of the fluid at that particular point. So this is volume stress. Then we have shear stress. Suppose there is a body ABCD and it is subjected to equal and opposite forces F at the top face and the bottom face, and due to these forces the body gets deformed like this. The body gets deformed like this. So you will notice that the two forces that are acting are equal and opposite, but the face AB is held, it is not allowed to move, and the face CD moves in this manner. So the force F divided by the area of this face. So to give you an idea, when I say area of this face, the diagram actually looks like this. So when I say area of the face, I am talking about this area. So the force divided by the area of the face is known as shear stress. So these are the three types of stress: longitudinal, volume and shear. Similarly, we have longitudinal strain, volume strain and shear strain. Longitudinal strain, volume strain and shear strain. Suppose this force is F, then the longitudinal strain is defined as, you can see that the force is going to elongate the body. So longitudinal strain is change in length by original length, so delta L by L. Similarly, this element of fluid on which the force acting is F, so for this element of fluid, the volume strain is change in volume by volume. Now usually the volume strain we take it as negative, because usually when you have an increase of pressure, it is followed by a decrease of volume and vice versa. So in volume strain generally we put a negative sign. Regarding shear strain, the angular displacement is theta, and if theta is a very small angle, then you can approximately say that theta is equal to x by h, that is known as shear strain. So longitudinal strain, volume strain and shear strain. Now stress and strain are usually proportional to each other, provided the strain should not be too high. If the strain is not too high, then stress and strain are usually proportional to each other. So, first thing is, there is a law for this. It is called Hooke's law. According to Hooke's law, if the deformation is small, then stress is proportional to strain. This is Hooke's law. Now, we can first talk about longitudinal stress and longitudinal strain. So the ratio F by A by delta L by L is known as Young's modulus for that particular material. So if you are talking about longitudinal stress and strain, then this ratio is called the Young's modulus for that particular material. Similarly, the ratio of F by A to X by H, that is shear stress to shear strain, is denoted by eta. This is called the shear modulus of rigidity or torsional modulus. Shear modulus, modulus of rigidity or torsional modulus. Then again, the ratio of P to minus delta V by V is known as bulk modulus, and the reciprocal of bulk modulus is called compressibility. Suppose there is a wire and the wire has been subjected to an elongation. So usually it is found that if you subject the wire to an elongation, then the diameter will decrease, whereas its length will increase. So when you subject the wire to an elongation, thanks to the fact that volume of the wire is a constant, so if you subject it to an elongation, the length will definitely increase but the diameter will decrease, and this ratio is known as the Poisson ratio. So the Poisson ratio for that material is, you can say, lateral strain by longitudinal strain is equal to Poisson ratio. Now, there is a very, very important graph . There is a metallic wire and it is being subjected to a stress, and this is the stress strain graph. Now the portion from O to A is called the proportional region. So in the proportional region, stress and strain will be proportional to each other. Then the portion from O to B is called elastic region. So why is it called elastic region? Because up to the point B, if you remove the cause of the stress, the strain will be also completely reversed. Now, if you suppose go beyond the point B, suppose to a point C, then if you completely remove the stress, the strain will not be completely removed. In fact, there will be a permanent set. There will be a permanent set, and the portion from B onwards is called plastic region. So anything which is not elastic is considered plastic. So beyond B, it is called the plastic region. And D is called the fracture point. You will notice that in the plastic region the graph reaches a peak. So after this, the material, although it is a solid, it starts flowing like a liquid, and finally when it reaches the point D, it snaps. So D is known as the fracture point. Now the thing is, if there is a huge gap between B and D, so if BD is large, then we say that the material is ductile, and if the portion BD is small, then we say that the material is brittle. So if BD is very large, we say it is a ductile material, and if BD is small, we say it is a brittle material. Now, there is a very interesting comparison in our day-to-day life. When we consider a material like rubber, we say that it is highly elastic. In fact, the stress strain graph for rubber is something like this. And the thing is that although it is elastic, but it doesn't follow the Hooke's law. So, in fact, even when the strain is 8 times the original length, if you leave it, it will regain the original length. So in that respect, rubber seems to be highly elastic. However, for a particular strain, the stress required for steel is greater than the stress required for rubber. So for a particular strain, the greater stress is required for steel. That means the internal forces which develop within steel are stronger than the internal forces which develop within rubber, and therefore steel is considered more elastic than rubber. And by the way, the most important yardstick for elasticity is the Young's modulus. The Young's modulus of steel is more than that of rubber. Now we come to the energy considerations. Suppose there was a wire, it has been elongated by x from its natural length. So the force which has caused the elongation is given by this. So the work that is done by the force for a further elongation dx is given by this. So W is integral 0 to L Ay by L into x dx. So W is equal to this. So this is the work done by the force F. So the total work done for an elongation small l is this. So finally we are getting one formula, half into stress into strain into volume. This means that whenever a wire is elongated beyond its natural length, then the work done for the elongation is stored as potential energy, and the formula is half into stress into strain into volume. So this brings us to an end of this session of elasticity.